Lesson 7.3, Proving Triangles Similar. Now, don't confuse this with proving triangles congruent. Congruence and similarity are different. Congruence means all the angles and all the side lengths are exactly the same, whereas similarity, it's a dilation, either smaller or bigger, of the triangle. So it says the measurements of two triangles are shown. Are the triangles similar? So remember, a dilation. So if you look at these angles, 60, 40, then hopefully using the triangle sum, you can figure out that third angle on both of those. And then you have 32 compares to this 40. Those are corresponding parts, or mark the corresponding shapes in the same color. So 30 corresponds, or 32 corresponds with 40. 24 corresponds with 30. Notice I'm picking like left side of the triangle, left side of the other triangle. Now they're not always going to be left and right because the shapes could be rotated, but just be aware of that. You want to find corresponding parts. So 36 corresponds with 45. You need to figure out if these are similar, and based on the previous lesson, you need to find out if their ratios are the same. Here's a construction. Would any triangle with two angles measuring 40 and 60 be similar to triangle ABC? So there's a picture of triangle ABC down here. And you have to create another triangle with 40 and 60 degrees and determine whether it's going to be similar or not. Example 1, establishing angle-angle similarity theorem. So we're going to kind of go over the theorem on how it works, and then we're going to talk about the actual theorem. So if you have two angles, like for example, A and R, those two angles are congruent. And you have angle B and angle S. Those two angles are congruent. Go through this solution, and it shows you step by step why those two triangles would actually be similar just by having two angles that are congruent, two corresponding angles. So try it. If A is congruent to R, A is congruent to R, and C is congruent to T, would those be similar, different angles? Would those be similar in different locations? Okay, hopefully by now you understand that the angle-angle similarity theorem is an actual thing. If you have any two angles congruent to any two corresponding angles of another triangle, those two triangles will be similar. So any two angles congruent to any two angles on the other figure, other triangle, I should say, then the two triangles are congruent. And there's a proof of it in exercise 10 if you want to look at that. So now we're going to talk not just angle-angle similarity, we're going to talk about side-side similarity. Example 2, if you can line these up and line them up with corresponding parts, LM corresponds with PQ, etc., is there similarity transformation? So you have to figure out, is there a way you can map one of those triangles onto the other? And you can go through this step by step. It kind of walks you through it. And basically it says, hey, you know what? There is a way. There is a way that we can map one of the triangles onto the other. And what that means is if their sides are proportional, they all have the same ratio that equals the same given scale factor, then those triangles are indeed similar, and that's the SSS, or side-side-side similarity. So if two of the corresponding sides are the same scale factor, or the ratios are congruent, and if they have an angle that is congruent, is the similarity transformation that maps onto those. So again, you can map them on visually or in your head, and then check your answer to see, well, does it work if it's two sides and an angle? Let's check. Okay, here's the first rule. Side, side, side similarity. So we've already gone over angle, angle. So that's one of them. In fact, I'm going to write them right here on this side so that you can remember triangle similarity rules. Similarity rules. Okay, now if you think back to a previous topic, we did congruent rules, and there was 5 of them: side, 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 angle, side, angle, angle, side, and HL. Those prove that triangles were congruent to each other. These are not the same. These are showing that triangles are similar to each other. So one of them we've already done is angle, angle. And so to not get confused with the congruent rules, we're going to put a little symbol here. So we're like angle, angle, similarity. Okay, here's another one, side, side, side. So this theorem also works. If we can prove that all 3 sides the ratios are congruent or the same scale factor, then we have a side, side, side similarity. Make sure to put that similarity symbol so you don't get them confused with the congruent triangles. So if all three sides are proportional, then yes, those triangles are similar. And this next one, side angle side, so same idea. And from that one last example, if you have two sides that are proportional, same scale factor, and the angle in between, notice the angle has to be in between. We've talked about that order in the past. So that's another rule, side angle side similarity. Those are the only three. So those three rules, angle angle, side side side, and side angle side, can prove triangles are similar. To verify that a triangle is similar to another triangle, if you're asked, are these triangles similar? So look, all three sides are given. So you need to figure out, is the scale factor from one corresponding side to the next congruent to all three sides? So let's look at this solution. First, you set it up. So again, you can color code. So if I take, and honestly, sometimes color coding is the best way. This 3 matches up with the 4.5. Notice that's that first fraction. Okay, and then they take BC, different color. BC corresponds with EF. That's that third one, or second one, sorry, that's that second one. And then if we pick one more, this 5, and I know that yellow is kind of hard to see, corresponds with that 7.5, and that's this ratio. Notice they all equal 2/3. Therefore, these triangles are similar because all three sets of corresponding sides are the same scale factor. This one's a little bit more tricky. It says, are these triangles congruent? PQS. So I'm going to start and I'm going to look PQS. So that big triangle, is it similar to RQP? Sorry, I keep opening that. So I'm going to redraw these so that they are all sitting in the same direction. So I'm going to go like this. And this is the bigger triangle. I know I'm not the best drawer. PQS, is that the same as, and I'll switch colors, so that's this outside large triangle. Is that the same as, or similar to, and I'm going to draw them the same, so they're facing like the same direction. This would be, notice the order, P corresponds with R, so I would have to put the R right here. Q, that second letter, corresponds with Q, so Q would go right here. And that third letter, S, has to correspond with P, so P would have to be right here. Now that I have them all labeled, now I want to label them with actual numbers. So I'm going to look what's given. This SQ at the bottom here is 15 plus that 12. That's that total length right there. Okay, PQ is 18, that was given. And then if I look at this smaller triangle, the green one, the PRQ, I have RQ as 12, PQ as 18. So the reason why, one, I drew them the same direction is so that they can line up the same so we can see corresponding parts. And two, if I don't have them labeled with the correct lettering or the vertices, it's going to get really confusing really fast. So that 15 plus 12, I'm going to say is 27. So I'm going to delete the 15 and 12. I just wanted them there so you could see them. And I'm going to say 27. Okay, so I've got two side links. And if I have those side links, I'm like, well, let's see if they correspond and the ratios are the same. So I'm going to say 27 corresponds with 18. Is that the same as 18 to 12? So I'm checking if their scale factors are the same. Now, keep in mind, I am taking the bigger triangle compared to the smaller triangle and seeing if that equals the bigger triangle compared to the other smaller triangle. So big to small, big part, like big at the bottom, small on the bottom, big triangle on the right, small triangle on the right. And I'm setting them equal and seeing, are those in fact equal? So if you need to, grab your calculator, but I know 27 divided by 18 is 1.5. So I'm going to say 1.5. Does that equal? And I'm like, okay, 18 divided by 12. That's also 1.5. So these are for sure the same scale factor. So I know they have the same scale factor, so I'm saying that two sides are similar to each other, but there's no rule that says side similarity. That doesn't count. So there has to be something else. So I'm going to go back and I'm like, okay, let's check the angles, because either I need a third side, which I don't have, or I need another angle. So I'm going to switch colors and I'm going to look for an angle. Angle S is right here, and that's right there. So I've got those. There's no angle S that same size in that green triangle. So I'm going to go look up here. This angle P is right here. Like, that doesn't really help. What I need is, if I can get angle side, where the angles come together, that would be perfect. So let's see if I can find that. This angle right here in orange, I'm going to put like a different marking, is RQP. RQP. It's right here. Okay, now, if I look at the big blue triangle, that is this exact same angle right there. So these two angles are exactly the same. They are right where angle Q is. That angle is identical. It's a shared angle. So by the reflexive property, those angles are the same, which means instead of this side-side similarity, which isn't even a rule, I actually have side-angle side similarity. And that is one of the rules that prove these triangles are similar. Here's the try it, same idea, see if they're the same, set them in the same direction. So A, D, E, notice order matters. So I'm going to draw a triangle. Let's draw it like this. A, D, E, A, D, and then E. And actually it's facing the exact same direction in the picture. A, D, E. So there's my triangle. And then I need to have it to check if it's similar to A, B, D. So A, B, D. Now just looking at it, it does not look similar, but that doesn't mean much. So I'm going to draw another triangle that looks kind of the same as the triangle I already drew. And then I'm just going to label it where the order matters. So A is up here. B, notice B is the second letter. D is that second letter, so that's the corresponding spot. And then other point D is right here. Okay, so I'm going to look at that and say, okay, now I've got to label everything accordingly. So on this purple triangle, DB is 2.4. AD is 2.4. And AB is 3.2. So I've got them all labeled on that purplish triangle. And now I'm going to go to the teal one, AD 2.4. And again, this is not anything earth-shattering. I'm literally just copying the picture, but I'm redrawing them so they're right next to each other, facing the same direction. Most kids who don't do this get these kind of problems wrong. So get in the habit of just drawing one triangle that it's easy to see, then drawing another triangle that kind of looks the same, but then worry about the measurements, like right here, or like the location of the letters, what order they go in, and then label accordingly. In this case, I'm doing small to big, so I have small triangle to the big triangle. Is that the same as the small to the big triangle? And is that the same as the small to the big triangle for every single side length? So I've got 1.8 over 2.4, and I'm just going to put a question mark. Is that the same as 2.4 over 3.2? And is that the same as 1.8 over 2.4? Now, nice thing to know, these two are exactly the same. So I don't have to figure those out twice. Okay, so grab that calculator, see what you get. Take a second and figure that out. Okay, hopefully I gave you enough time. If not, stop the video if you don't have it yet. So I am going to write on here what I got. I got 1.8 divided by 2.4 is 0.75. For this one, I got 0.75. And this last one, I should have gotten the same as the first, 0.75. So if I look, all three of these ratios are the same. So are these triangles similar? Yes, they are, by side, side, side similarity. And then you do the part B by yourself. Starting with example 4, we get a lot into the mathy type problems. I like these. What is MN? So you are actually finding the length of a missing piece. Or you're finding the missing piece of this triangle. So MN, I'm going to look at this and I'm going to put some colors on here because I love colors. MN, and based on these tick marks that I'm looking at, and the markings that we already have, I think I'm going to set up this triangle where the math, this proportion or ratio, small to big, and I need to set it up to small to big. So they are telling you these triangles are similar. They didn't say it directly, but I know this 2 markings on the side and these 1 markings on the side, and these are vertical angles. By side angle side, these are similar. Okay, so they are similar. I know the proportions and the ratios should be the same. So I'm going to say small triangle, this 1 corresponds with 75. So 1 over 75 should be equal to, since they're similar, something, I don't know, x over 10. This is a flashback to middle school. Hopefully you know how to do this. If not, it's okay. So I'm going to take this and I'm trying to solve for x on this proportion. I'm going to cross multiply. So I'm going to get 1 times 10 equals 75 times x. You need to get x by itself. So you're going to divide by 75, but first multiply these out, which I know you can figure that out, but sometimes they're not that easy. So I'm going to say 10 equals 75x. Divide by 75 on both sides. Whoops, 75. And you will get the actual measurement. And yes, it will be a fraction, but that's okay. This next part of example 4, very similar, same idea. It says if the measurement of JL, so right here, if this changed to 150, how would that change this problem? And would you get a different value? Well, if that one measurement changes, then of course the whole problem will change. So I'm going to change this to 150. Set it up, they're still similar. 1 compared to 150, so small to big, equals x to 10. And you're still going to solve for that x, and you can say how it is. How is it different? How much more different is it? Like, is there a scale factor of those? And part B, again, has another change. JL, we're 20 instead of 10. How would that make a difference? So it's basically changing measurements within the problem and try to figure out how does that affect the problem and the final answer. I love these problems, these similar triangles. And so if the sun is ever involved, and it says in the little bubble right here, you can consider the angles in which the sun hits the tower to be equal. So down here, this little sun angle and that little sun angle that's created, the angle from the shadow going downward. And just so you know, shadows are always going to be on the ground, and they're perpendicular to the object that casts the shadow. So this person, perpendicular, 90 degrees, casting that shadow is on the ground. So Avery puts up a radio antenna in the yard. Ella tells him that the city has a law limiting towers to 50 feet. Notice we do not have the measurement right here. There's no measurement. We're going to figure out if this is 50 feet or less. So it has to be. So how can Avery use this length of his shadow and the shadow of the tower to show that it's within the limits? So these are similar triangles. I know because it's angle, angle, similarity. See these 2 angles? They are the same on the small triangle as they are on the big triangle. So I'm going to slide down and I'm going to do some math for you. Set it up. So these are similar triangles. So I'm going to take small triangle compared to big triangle. Small triangle compared to, I don't know that, so I'm going to call that x. Okay. So 5 to 40 equals 6 to x. We've got our proportions. Let's cross multiply. And once you have this set up, the setup is the geometry part about this problem, making sure you know how to set it up. From here on out, the cross multiplying, that's the algebra part of it. So hopefully you're good at that geometry part, setting it up. 40 times 6. So I've got 5x equals 240. Divide both sides by 5. And then determine, is this within the city limits? Is it 50 or less? Another part, this number 5, same idea, same shadow, same picture, but it's saying if the tower were 50 feet tall, so exactly 50, what would the shadow of the tower be? So figure out where you're going to do. Are you going to compare like base to height, height to base, big to small to big? Just be consistent. So last time I did small to big. So this time let's do base to height. Base to height, set them equal. base to height because these are similar triangles. So these bottom numbers, those are the bases. And these top numbers, those are the heights. Okay, those vertical numbers. So I'm going to do base of the small triangle first. Base of the small triangle compared to height of the small triangle. Notice they're together because if I'm comparing base and height, they have to be on the same triangle. Equals base, which is the x, to height, which is the 50. And when I cross multiply this, you can still get the same answer as if, and I'm going to switch colors, as if you did small to big. So as if I did 5 compared to x and 6 compared to 50, as long as you are consistent. So if I did small to big equals small to big, notice I did this in a different color so you can know the blue stuff is the base to height and the green stuff is the small to big. I would do 5 to x equals 6 to 50. When you cross multiply, you will get the same answer. X equals 41.6. I got 6 repeating. 41.6 repeating, and we'll say feet. And over here, same thing. I got x equals 41.6. Sorry, that camera's going crazy. 41.6 feet. They're the exact same. So consistency is key with ratios and proportions. So make sure you know what you're comparing, base to height or small to big triangles. Just be consistent. Okay, big picture, here it is. You've got 3 rules that prove triangles are similar. You have angle, angle, side, 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 and side, angle, side. Be really careful. Those are the only ones you're allowed to use to prove that triangles are similar. If it were me on my notes or in my book, I would write these down and make sure I would even write them down next to the congruent triangles so then you can see the difference. There's congruent triangle rules, there are 5 of them, or there are similar triangle rules, there are only 3 of them, and that's what we learned today. I hope that helps.